Hey, this is an introduction to binary for binary numbering system, and then we'll look at some units, and the following videos are going to be about how data is represented in a computer in binary, so different types of data. We first need to go through a bit of theory to do with numeral systems or numbering systems. So in everyday life we use decimal, also known as denary in this topic, so exactly the same thing, decimal, denary, what we use normally. So technically speaking, it's a base 10 numbering system, and that means we have 10 digits we use, 0 through to 9, so 10 in total. And the base comes from, when you have an exponent, the number at the bottom is the base, and then whatever it's raised to is the exponent. And if we go back to place value, so we're talking primary school maths here, which you don't really think about because it's too basic, but it is important for this topic. For column names, go up by a factor of 10 each time. So really this is saying 10 to the 0, i.e. 1, anything to the power 0 is 1. And then 10 to the 1 obviously is 10 and increases, so the exponent goes up 1 each time, but the base remains the same. So what we're really saying is we've got 9 thousands here, 4 hundreds, 10 fives and 6 ones, and add together you get a number. So this is important when we talk about binary, because binary is a base 2 system, meaning it's got only 2 digits, 0 and 1. So all data used or stored in a computer is represented by binary digits shortened to bits. So a bit is either 0 or 1. And all inputs to the computer have to be converted to binary to be used, to be executed, or to be processed. That's why the following videos are all about representing data, different types of data in binary. So we are going to look at representing numbers, of course, but because binary doesn't only represent numbers, it represents all types of data, images, videos, and so on. It's better to think of 1 and 0 as symbols representing true or false, and this allows us to do something called Boolean algebra, or logic, as we've talked about. And this is replicated in a computer with 2 different voltage levels, so it can be on and off, on being for 1 and off being for 0. But in reality it's probably more like 2 different voltage levels, so 10 volts and 5 volts. And that's why we use binary with computers basically, because it's so simple to do. We could use base 10, we could use decimal, but we'd need 10 different voltage levels, and there are certain logic we can do in binary which we can't do in decimal. One of the reasons why it's better to think of bits as symbols is because depending on the context, one bit pattern, i.e. a string of bits, could represent a number, a character, different types of data basically. So this bit pattern, just a long stream of bits, 0 and 1s, this could be anything. We've no idea what this could. It could be a number, it could be an instruction, depending on the context. It's better to think of it not as numeric values, but as things that represent other data. So just to look at some units for binary, so a way to express an amount of binary numbers. So a bit is a fundamental unit. You can't get any smaller than a bit. It's either 0 or 1. A nibble is 4 bits, so you've got to be careful. If you're thinking of it in terms of a number, you can get rid of the leading 0, but don't do that because again we're thinking of it in terms of symbols, so 0 does mean something. So 4 bits together. Then you have a byte, which is labelled with a capital B, there's not really a symbol for nibble, and this is 8 bits. Usually we're using bytes, not really using nibbles, but often we have a group of 8 bits here, but often we'll leave a space in between each nibble for reasons we'll come on to do with hexadecimal. Now it becomes more confusing than it should be, really. We have a kilobyte, which is a lowercase k and then a capital B, and this is 1,000 bytes. Then you have a megabyte, which is a capital M and a capital B, and is 1,000 kilobytes, so each go up by 1,000 each time. But the issue is, unfortunately, there are 2 kind of ways of dealing with these larger sizes. So whoever came up with these, so kilo and mega come from physics, right? But physics deals with decimal, not binary. So physics is in terms of tens, whereas binary is in terms of twos, which makes things difficult. So actually, we now should be using sizes called using binary prefixes. So like a kibibyte, as KIB, is 1024 bytes, and this is correct. You never really get 1,000 bytes. Due to the way binary works, you're always going to have, the closest number you're going to have is 1024. But unfortunately, whoever adapted this, whatever computer science did this, caused loads of trouble down the line by adopting the physics instead of defining it as it should be, which is 1024. And likewise, there's an equivalent one for megabyte, i.e. a mebibyte, MIB, which is 1024 kibibytes. So a similar theme goes along. You have a gigabyte, which is 1,000 megabytes. You have a gigabyte, which is 1024 mebibytes. You have a terabyte, 1,000 gigabytes. A tebibyte, 1024 gigabytes. And then you have a petabyte, which is 1,000 terabytes. and a pebibyte, which is 1024 tebibytes. So the binary prefixes definitely sound a bit more pathetic, but these are actually the correct ones basically. So if you see megabyte, you should assume it's 1000 kilobytes and not 1024 kibibytes, although people often get this wrong. So all they do is grow by 1000 each time. Make sure you remember the order, so it's the same order, K, M, G, T, B. It's the same order, it's just the names and the symbols vary a little bit.